Okay guys, so today we're going to continue talking about special relativity, and in particular how clocks can appear to be out of sync and how events that look to happen at the same time in one frame of reference won't look that way in another frame of reference, particularly a moving one. So let me start by painting you a picture. Let's say we have a clock, right? Boom, 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 6, boom, 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 boom. And then over here, we'll draw a light bulb, which is going to emit light. But before I do that, let's draw another clock. That's an ugly clock. We can do better than that. That's also an ugly clock. Okay, that's fine. 12, boom, 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 6, boom, 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 boom. Now, let's say that the distance from this clock to this clock is a distance L. In other words, this spot right here, I'll use green, we'll say that's x equals 0. And let's not use yellow because that's used for light a lot. Let's say this position, we'll call that x equals L. And this light bulb is perfectly, so right here, and right where the light bulb is, we'll say that's a perfect distance x equals L over 2. So the light is right in between the two clocks. Now once you turn on the light, we're going to have light waves be emitted in both directions. I didn't really draw this to scale very well, but the point is they're equal distance. So the light from the light bulb should reach both clocks at the same time and start our clocks. In fact, we can find the time. So the light takes time t equals 1/2 L, because that's how far it's going, over the speed, right? Distance equals rate times time. Boom. Well, the distance is L over 2, and the rate is c, because it's the speed of light. So that's how long it takes to reach the two clocks, if you're looking at it from a stationary perspective. But let's consider a moving observer. O. Well, what do we know? We know that x1 is the first event, and that takes place at 0. So that's this event. And then x2 is the other event, and that takes place at distance L. That's where the other clock is. And what else do we know? Well, we know the time for event 1 is the same as time for event 2, which is L over 2c. We just found that above. Well, if you remember our equation, we can find out how long it took from a moving observer's point of view. We worked this out when we dealt with the Lorentz transformations. So what is it? If you remember, I'll write it down real quick. We'll do it in, I guess, red. T prime equals T minus ux over c squared all over the square root of 1 minus u squared over c squared. Okay? So let's look at the different events. Let's look to see from a moving observer's point of view for event 1, which is the light hitting the green clock. That will be equal to T1, the stationary observer, minus u over c squared all over the square root of 1 minus u squared over c squared. And then there's an x at this part. But x position for 1 we said is 0. So that's times 0. So this whole bit goes away. So that simplifies nicely to T prime 1 equals T1, which we said was L over 2c, divided by the square root of 1 minus u squared over c squared. Okay. So this is how long a moving observer measures the time it takes for the light to get there. Now, there's also the second event, which is t prime 2. And that's equal to, using the same means, oops, that's supposed to be a c. We're using the exact same equation, the only difference is the t changes from t1 to t2. But t1 and t2 are the same, so it actually doesn't matter there. And the x is different. So if we were to write this out, if we were to continue doing this, t prime 2 equals, well, time 2 we said was was L over 2c, right? That's t2. Minus u over c squared times x, which we said was L. And then that's all over the square root of 1 minus u squared over c squared. So right off the bat, we have this. This is the time it takes for the light to hit the other area. And then we also have t prime of 1, which we said was L over 2c divided by the same denominator, 1 minus u squared over c squared. This was our other one, right? Well, which one is bigger? Well, I think it's obvious that t1 prime is greater than t2 prime. Why is that? Well, let's start by saying they both have this. We're both dividing them by the same number, which is the square root of 1 minus u squared over c squared. Right? That's the same for both of them. That doesn't change. The speed of light doesn't change, and u's just however fast our observer is moving. Okay? I'm not going to color it all in, but you get the idea. They also both have an L over 2c, right? And that's because the event 1 and event 2, they both reached at the same time from the perspective of someone not moving. The difference of it is here. This one, you're taking u times L over c squared away from our numerator, or you don't do that for t1. So t1 is going to have a bigger numerator, and because of that, it's going to be a bigger overall number because everything else is the same. And in fact, we can find delta t prime because that's just going to be t prime 1, our bigger number, minus t prime 2, our smaller number. Or L over 2c divided by the square root of 1 minus u squared over c squared minus L over 2c minus u squared over c squared, UL over c squared, square root 1 minus u squared c squared. And if we wanted to simplify that, that'll be L over 2c minus L over 2c plus UL over c squared, all over the square root of 1 minus u squared over c squared. They have the same denominator, so it's pretty straightforward. These drop, and we can say delta t prime is equal to UL over c squared times the square root of 1 minus u squared over c squared, right? Which, if we really want to, make it look nice, UL over c squared square root 1 minus u squared over c squared. And that's the difference in time between event 1 and event 2. So event 1, we said, was a bigger number. Time 1 was a bigger number, right? So that means this event, t2, happens first. So because that happens first, this time over here that we just found tells you the delay, basically, from when we observe event 1 and event 2. So what's the point? The big point is, and what we want to mention is two events that are simultaneous in one, I want to say point of view, but essentially I mean reference frame, is not necessarily, it doesn't have to be, is not simultaneous in another point of view. So a bit weird. There's a lot of weird stuff, and we're going to start talking about that more and more. And I think we're going to talk we have a couple more videos, and then we're going to get into dynamics. So that'll be fun. Hopefully this helps, and this makes a little bit of sense. And I just want to mention before I do this isn't time dilation. This is just the delay. So hopefully that makes sense.